Imagine how you normally program. When you write a program, you usually tell the computer what to do step by step. Change variables, use loops to repeat actions, save results somewhere. Here's an example in Python. This is called imperative programming. You focus on how to do things. Now think about describing what you want. Instead of focusing on how, functional programming asks you to describe what you want. Here's an example in functional style. Here you're saying map this function n to the power of 2 over the list of numbers. You're skipping the explicit loop, the variable updates, and the manual appending. So what makes functional programming different? Firstly, there's a focus on functions. A function in math terms takes an input, does something, and gives output. For example, f of x equals x times x. Every time you pass 2 to f of x, you get 4. Functional programming builds on this idea. And secondly, no changing things, otherwise known as immutability. Data does not change after it's created. Instead, you make new data. Imagine you have a grocery list. Instead of crossing out milk or modifying it, you make a new list without milk. So why is this even useful? When programs get very large, bugs often happen because of two things. One, a variable was accidentally changed somewhere, and two, it's hard to keep track of what is modifying what. Functional programming avoids these problems. There's no sneaky changes to variables because everything is created from scratch, and functions also behave predictably. There's this key idea of pure functions. It's a function that only depends on its input and does not affect the outside world. Here's an example of a pure function. Contrast this with a function that changes a global variable and is thus not a pure function. Notice that the global total variable is being modified within the function. The second concept is higher order functions. A higher order function is a function that takes another function as input, or returns a function as output, or does both. Here's an example of a higher order function taking a function as input. Think of a scenario where you want to apply some operation to every number in a list. Instead of writing a loop every time, you can use a higher order function like map. Map is the higher order function because it takes double, which is another function, as its input. It applies double to each element in numbers for you. You can see in the output that we have doubled all the items in the numbers list. In example 2, we have a higher order function returning another function. Sometimes you want to create a new function with customized behavior. A higher order function can return functions. Here, multiplier is a higher order function because it returns another function. The return function, called multiply by, remembers the factor you provided. So notice that in this line we create a function that multiplies by 2, and in the following line we call the function that has been returned by the higher order function, which multiplies our argument of 5 by 2 and outputs 10. The reason we use higher order functions is because they reduce code duplication, and it also makes code easier to read by abstracting common patterns like mapping, filtering, or reducing. There's a couple common higher order functions. We have map, which transforms each element in a collection. There's filter, which keeps elements that satisfy a given condition. And there's also reduce, which combines elements into a single value. Here's an example of each. Using map, we double every number. Using filter, we only keep even numbers. And using reduce, we sum up all numbers. In functional programming, we also avoid loops using recursion or abstractions. So instead of writing loops, functional programming uses recursion, for example, functions calling themselves, or tools like map and reduce. Here's an analogy. Think of functional programming as baking. We have a recipe, which is a function, in which you follow steps and always get the same cake if you use the same ingredients. And there's also no leftovers, which means no side effects. The recipe doesn't leave a mess in the kitchen, everything is contained. And there are reusable instructions, or modularity. You can reuse parts of the recipe, like the steps for making frosting. So the recipe represents a pure function. Same input always gives the same output. No leftovers implies immutability and avoiding side effects. Functions don't modify outside state. And reusable instructions reflects higher order functions and composability. Functions can be reused and combined very seamlessly.